Hello, the objective of this lecture is to introduce combinations of loads and how they are handled in the design of civil and architectural engineering structures. Let's get started. So now that we have an understanding of what the different load types are and an understanding of the load and resistance factor design philosophy, we can talk about the development of load combinations. Now, every structure that we design, at least everyone that I can think of, has to be designed for several concurrent loads. It wouldn't be practical to design just a building for dead load or just a bridge for live loads or just something for wind loads, etc. You have to design for the possibility of each of these to happen in combination with another. So the trick is, though, to figure out which combinations you should design for. You could really go crazy on this and design for, a 50-year snow event acting at the same time as you have a 50-year wind event during a rock concert where you have the maximum live. You just have to consider what is the probability of all those things happening at the same time. So that's what the purpose of load combinations is. To this end, we categorize our loads as permanent loads, loads that are either variable or transient, loads that are environmental or meteorological, and at least for my purposes, I'm going to categorize earthquake loads as their own entity. I think Tally and maybe even Finella categorize them as environmental loads as well, but I'm going to treat them a little bit differently. So where this is coming from is the idea that for the load and resistance factor design philosophy, we have the governing equation that the sum of gamma times Q has to be less than or equal to phi times R sub n. Right now, we're focusing on the development of the left-hand side of this equation. We're focusing on the sum of gamma times Q. Load combinations are the sum of gamma times Q. So the load factors that we develop are typically going to be either greater than or less than 1. If a load effect is leading to the design of the member, making the demand worse, then the load factor is typically greater than 1. If the load effect is helping the member, making the load demand lighter, then the load factor is often less than 1. Okay, earthquake and wind loads are a little bit different than that. Earthquakes and wind loads are calculated at their maximum lifetime load levels, whereas the other load effects, dead, live, snow, and rain, are calculated at their arbitrary point in time levels. So when we include E and W in our load combinations, they're often calculated using a load factor of 1. Now, different textbooks and different standards use different terminology, but a lot of times you'll see the term strength level loads for earthquake and wind. It also bears mentioning that if you go back to the last couple of versions of ASCE 7, that I think the 2010 edition of ASCE 7 included a load factor for wind of 1.6 instead of the 1.0 that you'll see now. And if you go back a few versions before that, the load factor for earthquake was also 1.6. So they made a change over the past 20 years from calculating E and W at arbitrary point in time levels to maximum lifetime levels. Okay, the load combinations, the load factors that we're calculating for these combinations were developed using a first-order probabilistic analysis. They're based on a 50-year recurrence interval, and they're calculated using a broad survey of reliabilities that were inherent in contemporary designs. So basically, they looked at buildings that were designed using allowable stress design or load factor design, and they calibrated the load factor so that they would get approximately the same level of reliability out of the newer structures. Okay, these combinations are intended for the design of any structural member, regardless of the material. And they're intended to be used with resistance factors that are given in the material-specific specifications. So the idea is that you can use the same combined loads for any given building, and then go to the ACI specification and get the resistance factors for the concrete elements, and go to the AISC specification and get the resistance factors for the steel elements, et cetera, et cetera. that wasn't always true. Back in the 90s, when I learned steel design, there were one set of load combinations that were used with the steel LRFD specification, and a different set of load combinations that were used with the ACI specification. And that was a real headache when you had buildings that were made up of both steel and concrete. So that's been solved, and now you have one set of load combinations that, in theory, should apply to all the different elements in a given building, regardless of whether they're steel, concrete, or wood. Okay, and then finally, the combinations that we're going to discuss, at least initially, are not intended for serviceability criteria. They're intended only for strength. There are different load combinations for serviceability criteria. Okay, load combinations in general are constructed by one of two approaches. They're constructed either by starting with a dead load, adding one or more of the transient loads at their maximum lifetime level, and then adding the environmental loads at their arbitrary point in time levels. Or they're constructed by starting with the dead load, adding one or more of the environmental loads at their maximum lifetime levels, and then adding the transient loads at their arbitrary point in time levels. So the idea here is, dead load is a permanent load. It's always going to be there. You have live load, which is a transient load, and let's consider snow as the environmental load. It's rational to design for a rather large live load with a average snowfall, or it's rational to design for a rather large snowfall with an average live load. But it isn't really rational to design for the maximum live load that the building's ever going to see at the same time that you have the maximum snow load that the building is ever going to see. Odds are, if it's a 50-year snow event, that most of the people that would otherwise occupy the building probably won't be there. So that is the basic approach that goes into the development of these load combinations. So the basic load combinations that are in the ASCE 7 specific standard are given here. The first one is 1.4 times the dead load, and that's to address long span structures or structures that have a high dead to live load ratio. The second one is your basic, the basic design load combination where you have dead load and live load at their maximum lifetime levels, and you have the environmental loads L sub R, S, or R at their arbitrary point in time levels. The third load combination reverses that, so now you have the roof load, the roof live load, the snow load, or the rain load at their maximum lifetime level, and you have the transient loads at their arbitrary point in time level. Then we have combinations 4 and 5, which deal with wind. And then at the bottom, basic load combinations with seismic. You have load combinations 6 and 7 that deal with seismic. So with the wind load and the seismic loads, we have a plus or minus in there because the wind can blow either left to right or right to left. In fact, it's much more complicated than that, and we'll see that when we get to the wind load module. But you could have load blowing from east to west, from west to east, from north to south, from south to north. You could have wind causing a torsion. You can have all kinds of different effects. But anyways, if we consider a two-dimensional structure, then you could have wind either blowing in the positive direction or the negative direction. More than that, depending on the nature of the wind and the way that it affects the structure, it could cause an uplift as well. So we have two combinations. Number 4 is for the case where wind is causing compression in I'm sorry, let me restate that. Number 4 is where the case where wind is causing loads that are additive to the gravity loads. So compression in a column that adds to the compression due to dead load, for instance. Load combination number 5, however, is for the case where the wind load is acting in the opposite direction of the gravity loads. So on the windward side of a large building subjected to overturning, you're going to end up with tension in the columns due to wind load, and that tension would act to reduce the compression in the columns that would otherwise be felt due to the dead load. So we have a 0.9 factor in front of dead instead of 1.2 in that case, because the dead load is creating force in one sense and the wind load is creating a force in the opposite sense. The same thing is true for the seismic loads as well, except with seismic, we break it down explicitly to consider the horizontal effects separately from the vertical effects. So you have E sub V, which is the vertical earthquake effects. So when it's additive to the gravity loads, you have a 1.2 factor in front of dead. And when it's negative, when it's negating the gravity effects, you have a 0.9 factor in front of dead, and the live load and the snow load don't appear there. Okay, lot to be said about that. So if we look at some of the details associated with this, we have 7 load combinations, but in reading some of the details in the ASCE7 standard, you'll note that the load factor on L in combinations 3, 4, and 6 is permitted to be taken as 0.5 for all occupancies in which L0 is less than or equal to 100 pounds per square foot. Now, we don't know a lot about live load yet at this point, but L0 is the unreduced live load. And the live load that we design for is often in the range of 50 to 70 pounds per square foot. So occasionally 100 pounds per square foot. Only in rare cases does it get up higher than that. So for most of our occupancies, we can design for 0.5 times L in those load combinations. Okay, also to be considered is the idea that the effects of one or more of the transient loads not acting shall also be considered. So in some cases, it's more critical if the live load isn't there, or it's more critical if the snow load isn't there. So let's take this 2-span beam, for example. We have a uniformly distributed dead load, and that's going to lead to the case where we have a positive moment in the main spans and negative moment over the center support. So let's suppose that we're designing for a live load that would be distributed like this normally. But if we have all 4 of those point loads that represent the transient load acting, that's not the most critical case when you consider positive moment. If you were to design for just the 2 loads that are in the first span, that would lead to a higher moment, a higher positive moment in the first span. Or if you were to design for just the 2 loads in the second span, that would actually lead to a higher positive moment in the second span. But the case of all 4 loads acting together would lead to the maximum negative moment over the middle support. So you have to consider different permutations of transient loads acting on. Okay, there are also other numerous permutations to these combinations as well. For example, in combinations 2, 3, and 4, you consider either the roof live load or the snow load or the rain load. You have the plus or minuses that are associated with the wind load. It could act to the left or to the right. You have the plus or minuses that are associated with the horizontal earthquake force, et cetera, et cetera, et cetera. So one way of boiling this down a bit is if we take R as the governing roof load, instead of saying R is the rain load, we're going to say R is the maximum of either the rain load, the snow load, or the roof live load. Then we end up with these permutations for the load combinations. So you have one version of load combination number 1, you have 2 versions of load combination number 2, you have, So these are basically the load combinations that are boiled down when you consider a 2-dimensional structure and consider the directionality of the wind and the seismic. So it doesn't take too long for all these load combinations to really blow up. All right, if we look at the International Building Code instead of ASCE 7, there is a set of load combinations there that at first appear like they are different. The first difference is that load combinations 5 and 6 are reversed. So the first thing that I'll do is I'll just flip-flop those and renumber it. Okay, after we renumber the load combinations, now at least they're in the same order. They have the same general approach, right? The dead load is the governing in the first. You have dead load plus 1.6 live in the second, dead load plus 1.6 times the environmental in the third, et cetera, et cetera. Okay, one other difference is that the International Building Code, the IBC load combinations, include the fluid load as a primary load effect. Now, at first that makes it look like they're different than the ASCE7 load combinations, but if we read the details in the ASCE7 standard, it says that where fluid loads are present, they shall be included with the same load factor as dead load in combinations 1 through 4 and 6 and 7. So if we take this and look at how that affects the ASCE7 load combinations, it means that the load combinations in IBC are the same as the ones that are in ASCE7. Another difference is that the IBC load combinations include horizontal earth pressure explicitly, right? The H load. Again, though, if we go back to the ASCE 7 standard, it says that where loads H are present, they shall be included as follows. Case 1, where the effects of H add to the primary variable effect, then you include H with a factor of 1.6. Where the value of H actually mitigates the primary variable effect, then you include H with a load factor of 0.9, where the load is permanent, or with a load factor of 0, where the load is not permanent. So if you consider the impact of these or of these provisions on the ASCE 7 load combinations, then again it makes the ASCE 7 combinations the same as the IBC load combinations. Okay, a third difference is the factors F1 and F2 that are in the IBC load combinations. Okay, if you read the details of the International Building Code, it says that F1 is equal to 1.0 for places of public assembly and places where you have more than 100 pounds per square foot live load. It's taken as 0.5 for other live loads. Reading on, IBC also says that you take F2 equal to 0.7 for roof configurations that don't shed snow, or you take F2 as 0.2 for other roof configurations. So the factor F1 is not in the ASCE 7 standard explicitly. However, there is a provision in ASCE 7 that says that we take the factor on L as 0.5 in most of the occupancies where the live load is not greater than 100 pounds per square foot. So if we take that, that means that F1 is the same in IBC as it is in ASCE 7. Okay. Further, if we look at the factor F2, it's also not explicitly found in ASCE 7, but there is a provision in ASCE 7 that says that for combinations 2, 4, and 5, the snow load shall be taken as the flat roof snow load, P sub F, or the sloped roof snow load, P sub S, depending on the configuration of the roof. So what that means is that, once again, the ASCE 7 load combinations are basically the same as the IBC load combinations. All right, so those are the LRFD load combinations. Now, if we look at the allowable stress design load combinations, they are presented differently. So we have the basic load combinations, 1 through 4. We have load combinations that deal with wind, 5, 6, and 7. And then we have the load combinations that deal with seismic, 8, 9, and 10. So the basic approach is the same as it is for LRFD, except that we are designing for loads at different levels because the factors of safety are different than the resistance factors. But the basic approach is maintained, right? We have dead load acting alone. We have dead and live load acting alone. At their arbitrary point in time. We have dead plus the environmental loads. Then we have the case of dead with live with the environmental loads, and they're a factor of 0.75. Then we have dead plus wind. We have dead plus live plus some wind plus some environmental, et cetera, et cetera, et cetera. Now, it's interesting. There are factors in here of 0.6 times W, and that's because the wind load W is calculated at the maximum lifetime level as opposed to the arbitrary point in time level. When you look down at the seismic loads, you have a 0.7 times E sub V and a 0.7 times E sub H. And again, that's reflective of the idea that the earthquake loads, E, are calculated at the maximum lifetime level directly as opposed to being calculated at the arbitrary point in time level. Okay, in the LRFD load combinations, there is a way of accounting for extraordinary events that aren't included in the basic load combinations. So these cover things like fires, explosions, vehicular impacts, blast loadings, and things like that. So these load combinations tend to look like the seismic load combinations, either 0.9 or 1.2 times dead, plus 0.5 times L, plus 0.2 times snow, and then you include this A sub K, which is the load effect that you're designing for. So if you're designing for a vehicular impact, then A sub K would be the force imposed on a member due to the vehicle impacting the structure. If you're designing for blast, then somehow you would quantify the member force due to that blast loading. Okay, we'll shift our attention to serviceability right now. The LRFD load combinations and the allowable stress load combinations, um, they don't cover serviceability. They're only for the strength design of the members. So let's look at IBC for the moment. Section 1604.3 says that structural systems and members thereof shall be designed to have adequate stiffness to limit deflections as is indicated in this table. So this table is, it's only part of the table that actually appears in IBC. It's the part that I thought was most interesting. And it limits deflections of beams. So the deflection limits are interesting, but they're really not the point of this slide. We have the deflection of L over 360 if you have a member supporting plaster or stucco, et cetera, et cetera. What's interesting are the loads that are being used to evaluate the deflections. So in some cases, we're using the live load or the roof live load. In other cases, we're using both the dead and the live load. And then in the third case, you're using the deflection due to snow load or wind load. So there aren't explicit load combinations given, but in this table or in this section of IBC, it alludes to the idea that we're using the service loads or the nominal loads or the loads that we would expect at any arbitrary point in time, with the exception of W, and I'll come back to that in a second. If we look at ASCE 7, Appendix C of that standard includes serviceability considerations, but these are not a mandatory part of the standard. They do provide guidance for the maintenance of the function of the building and the comfort of the occupants during its normal use. It covers things like vibration, drift, and beam deflections, things of that nature. Okay, and it says that serviceability shall be checked using appropriate loads for the limit state being considered. But it doesn't go on and give you any idea of what the loads should be. So there's a lot of latitude left here to the engineer of record in deciding what constitutes appropriate serviceability and what loads the serviceability's limits should be checked at. It does go on and say that camber is necessary. So what camber is basically where you take a beam and you bend it upwards before any loads are applied, so that when the dead loads are applied to it, it deflects into a flat or horizontal orientation. So the idea would be if you took a perfectly straight beam, let's say made out of steel, just for sake of conversation, and you suspended it between two columns, it would sag a little bit under its own weight. And then you add the weight of the concrete for the deck and for the other loads, that beam would actually sag possibly by as much as 1 inch or 2 inches in the middle, depending on the span and the stiffness of the beam and things of that nature. That might make the floor unusable. If you had a piece of machinery in there or a piece of some equipment that required the floor to be flat, then it would be unworkable. And at best, it's just not a good situation. So typically, we'll camber the beams upward. We'll bend the beams upward so that when the dead loads and maybe a portion of the live loads are applied to the beam, that the beam deflects down into a flat position. That's what camber is. Okay, there are lateral drift criteria in IBC. It states that drift limits applicable to earthquake loads shall be in accordance with ASCE 7. Now, drift due to earthquakes is a bit out of our scope right now. We'll come back and touch on that towards the end of the semester, but for right now, I'm not going to deal with that. But wind drift is not. Wind drift criteria is not included in IBC or ASCE 7, but it is often checked. Sometimes we compute the drift due to a 10-year wind event instead of a 50-year wind event like we would for strength design. And oftentimes you would estimate the 10-year wind event to be 70% of the 50-year wind event. So that's often used as a loading for establishing drift criteria due to wind. All right, now those are the combinations for buildings and other structures. AASHTO has its own set of load combinations. Now, the loading that a bridge is subjected to is fundamentally different than the loading that a building is subjected to, right? You don't drive trucks across buildings most of the time. So the load combinations for bridges are different. They're broken up into different limit states. The strength limit state is basically the same as the strength load combinations from ASCE 7 or IBC. You're talking about the member strength or the strength of individual components of a bridge. So you can see here they're presented in a tabular format where you have a value of gamma sub p for the load factor on dead loads, and that varies depending on the type of dead load. You use 1.25 for DC, the weight of the bridge components and attachments. You use 1.5 times DW, the weight of future wearing surface and utilities. The live load and the impact factor due to the live load gets a factor of 1.75 in strength 1. I'll come back and talk about what each one of these addresses. So the strength 1 load combination is a basic load combination relating to the normal vehicular use of the bridge without wind. Load combination 2 is for owner specified vehicles. So if you're going to do a load rating or an evaluation of the structure under a permit vehicle, you would use load combination number 2. Load combination strength 3 is for the most severe wind event in the 75-year design life of the bridge. So in that case, you wouldn't expect much live load. Strength 4 is there for cases where you have a large structure with long spans where the dead load is playing a bigger role than it would in the design of most other structures. And then strength 5 is for the case where you have, say, a 10-year wind event in normal traffic. Under that case, you wouldn't expect the heaviest truckload in the life of the bridge to cross during a 10-year wind event. Okay, so the bottom line is for components not typically governed by wind, you use, not typically governed by wind, strength 3 and strength 5 don't need to be checked. And strength 1 is typically the one that governs. Okay, here are the load combinations for serviceability checks. You have service 1, 2, 3, and 4. So you have a load factor of 1 on the dead load, and the load factor on the live load varies between 1 to 1.3 to 0.8. Okay, service 1 is there for normal operational use of the bridge. You use that to check things like compression in precast concrete components. Service 2 is to check load combinations intended to control yielding in the structures and to check slip-on connections. And then service 3 and 4 are there to check crack control in pre-stressed concrete. And then finally, we have 2 extreme event load combinations, 1 and 2, and you have 2 combinations to check for fatigue. So the extreme event 1 load combination is addressing earthquakes. And extreme event 2 load combination deals with things like ice in a river, collision by vessels, barges and ships and things like that. And then fatigue 1 and fatigue 2 deal with the fatigue issues associated with bridges. Fatigue is a driving factor in bridges. It can be in buildings as well, but isn't always. It's less often a driving factor in buildings. So you can see that the basic approach is similar. You have the strength combinations that deal with combinations of permanent loads, transient loads, and environmental loads. And then you have seismic and extreme event handled separately. Then you have serviceability criteria that's probably better addressed in the bridges than it is in the buildings. All right, so what this all boils down to is if you're looking at a steel structure, you design for strength 1, service 2, and the 2 fatigue load combinations. So in strength 1, you would have 1.25 times the dead load plus 1.5 times the weight of future wearing plus 1.75 times the live load, which includes the dynamic effects. Then you would check serviceability criteria using dead load plus 1.3 times live load. For the design of pre-stressed concrete, you would have these load combinations to deal with. And then the design of reinforced concrete, you would use these load combinations as well. Okay, so hopefully by now you have a really good understanding of the different types of loads from the first lecture. I have an understanding of the basic reliability approach to load and resistance factor design from the second lecture, and then from this lecture, understand how the load combinations are put together and how all the pieces of this puzzle fit together. So we'll spend the rest of the semester, much of the rest of the semester anyways, talking about how to calculate the loads, how to figure out what the dead load is going to be, the live load, snow, rain, wind, etc. And then in follow-on classes, we'll talk about how to design the components. There's several classes addressing steel design, several addressing concrete, one class addressing bridge design, etc., etc. All right, thanks.